Today, we know that light travels through a vacuum at a specific speed, and we even know what that speed is. In fact, we also know that the speed of light is not just any number. It's the fastest anything can travel in the universe, the universal speed limit. But it wasn't always obvious that light had a finite speed. In most practical situations, light sort of seems to travel instantaneously from one place to another. So at least as far back as the ancient Greeks, early philosophers and scientists were split over whether or not they thought light had a measurable speed at all. That was an open question for centuries at least, until a 17th century astronomer stumbled across a clue in Jupiter's moons that finally settled the case. A long line of people before that had attempted to get an answer, though. Even Aristotle, back in ancient Greece, took a swing and a miss at the question. He reasoned that we could detect delays in sound, but light seemed to get places without any time lapse at all. Meanwhile, other philosophers argued that no, light can be fast, but it can't be infinitely fast. Get it together, Aristotle. Finally, some scientists tried to break up the philosophical fight with actual data. In the early 1600s, Galileo and an assistant stood some distance apart holding covered lanterns. First, Galileo would uncover his lantern, then the assistant would uncover his as soon as he saw the light from Galileo's. When Galileo saw the assistant's light, he would note how much time had passed. They even tried this at different distances to try to separate out the speed of light from their reaction times. You've got to give the guy credit, but the results were still inconclusive. Galileo wrote that if light didn't move instantaneously, it was at the very least extraordinarily rapid, at least 10 times the speed of sound. But the first person to prove that light had a speed limit actually wasn't trying to measure the speed of light at all. In the 1670s, the Danish astronomer Ole Romer had been commissioned to create a chart sailors could use to determine their longitude, that is, how far east or west they were while they were at sea. They already knew how to measure their latitude using the positions of the stars, but to calculate longitude, you had to know exactly what time it was, and old clocks weren't very good at keeping track of that on the high seas. Over time, they accumulated lots of errors. So Romer was trying to come up with a different way for sailors to keep time. Earlier that century, Galileo suggested that it might be possible to use the 4 known moons of Jupiter as a celestial clock. Since they all orbited Jupiter in a matter of days, Galileo thought it might be possible to keep time by tracking when the moons passed over their planet. Each of these mini eclipses would be like a very slow tick of a clock. And as weird as that sounds, Romer was on board. The plan was to create a table documenting the exact times those eclipses happened according to the clocks at the Paris Observatory. Then, each time they saw an eclipse, sailors would be able to look up the exact time it was scheduled to happen and reset their onboard clocks to that time. Romer set to work with Io in particular since it has the fastest orbit, just under 2 days long. Except while he was working on this, he noticed something weird. As the months went by, Io's eclipse was falling behind schedule, and then catching up, and then creeping ahead of schedule, and then falling back again, which was completely baffling. Celestial bodies don't just casually speed up and slow down like that. That's when it clicked. If light had a finite speed, it would take longer for the light from Io to reach Earth when it was farther from Jupiter, and less time when it was closer. And that was exactly what Romer observed. So the speed of light had to be finite. Once that was settled, Romer took the first steps toward estimating that speed. He knew that the difference between Earth and Jupiter's closest approach and their farthest approach had to equal the diameter of Earth's orbit. So over the course of about half a year, as Earth moved from one side of its orbit to the other, he measured a maximum delay of 22 minutes. The person to actually crunch the numbers and get the speed of light was one of Romer's contemporaries, the Dutch astronomer Christian Huygens. Using Romer's value for the maximum delay and a rough estimate of the diameter of Earth's orbit, he was able to calculate the speed of light using the basic physics equation that says velocity equals distance over time. And he came pretty close. He calculated a speed of about 211 million meters per second. Today, we know that the speed of light is roughly 300 million meters per second, so Huygens' calculation was a little off. That's because he didn't have a precise value for the width of Earth's orbit, and because the maximum delay Romer calculated was a few minutes too long. But hey, It's not bad for a 17th century astronomer who wasn't even trying to discover the speed of light. And as for Romer's original goal, well, it turns out you can't really see Io that clearly from a ship in the middle of the sea. So eventually people came up with a mechanical timepiece called a chronometer to figure out longitude. But it's a good thing that he tried, because along the way, he stumbled across a pretty important discovery. Thanks for watching this episode of SciShow Space. As you just saw, in the past, it sometimes took a lot of roundabout science to uncover knowledge that we think of as fundamental today, like the speed of light, and the fact that Earth goes around the sun, which we actually made a video about, which you should check out next.